Promises and perils of AI. I'm just showing you very briefly a reminder what we talked about. So in the field of computer science, there are many fields, among them the field of AI, but there are many other ones, of course. And within AI, you have machine learning, like other subfields. Knowledge representation, NLP, reasoning, planning, and so forth. But within machine learning, you have supervised learning, you have unsupervised learning, you have reinforcement learning, and within supervised learning, you have what we call deep learning, but other techniques as well, and I'll mention some of them today. Okay? So what you have to remember is that deep learning is within supervised learning, which is within machine learning, inside AI, which is a computer science field. They're not equivalent there, one inside the other. Now, everybody's talking about AI, and I said it's not a new field, it's just coming back somehow. The reason is that we have these three factors, massive collections of data, we have very sophisticated and powerful computers today, more than ever before, and we developed sophisticated algorithms that can take advantage of these computers and this data. What I also talked about is what machine learning is, and I told you what you have to just keep in mind is the fact that in supervised learning you have data that has been labeled. I'm representing labels here with colors. We call training data. We later will have data that is not labeled, so this is labeled by experts. We give it to the computer to learn. The computer will go through it. I don't know why it's a square, it should be a rectangle. This is from my merging my slides. That algorithm that learns from the labeled data will create a representation of the learning. It's a model that helps it discriminate between the different classes. The classes here are colors. Okay, so the blues, the reds, the greens, the blacks, the grays. That model that has been created during the learning is used to automatically label these. That's what machine learning is. The machine here learns from this to then predict. We talk about predictions. It predicts what is the label that should be added to this. It's not an expert doing it like here. It's a machine that will do it automatically. Okay? That's what machine learning is. So that's what I talked about last time, basically, in a nutshell. So I stopped before talking about precision health, because that's where, well, we have the fact of medicine, and that's where machine learning is actually very, very helpful. And I say that machine learning is a catalyst actually for precision health. So what is precision health? Precision medicine basically refers to tailoring medical treatments to individuals based on individual characteristics. So each patient is different. So medicine is not only very personal, but today we put them all in the same cohort. If they have the same symptoms, we treat them the same way. But they are different. But they have the same symptoms, so we treat them the same way. What we would like to do with precision medicine is to divide them, even though they have the same symptoms, we divide them in different cohorts, as small as possible, and treat them differently. Because they respond differently to these treatments. Even though they cough and they have fever and they have the same symptoms. People are different. So people have been thinking about that for a while, and the first thing that comes to mind, what distinguishes us, our genome. So they focus on genomics, so microarray data, SNPs, single nucleotide polymorphisms, metabolomics, microbiomes, all these things that distinguishes us. But yes, this can be used for precision medicine, but it's not the only thing. We can also use other information that goes beyond the genetic stuff. So how can that work? Well, here's an example, very simple example. I have a new patient. That patient, I have information about that patient. And I want to know if the particular disease that I just treated will reoccur or not. Okay. Well, I can look at the history, the other patients that I treated before, and I have information about them. There are many dots everywhere, so that it's way bigger than that, okay, in terms of columns and in terms of rows. But for them, I have the information, yes, it reoccurred or not. Okay. From that information, which I don't have for this patient, well, I can predict it. How do I predict it? Well, I learn from this data. This is my annotation. These are the colors that I showed you before, blue, red, green, whatever. But here I have two colors. I have a yes and a no. So, like blue and red. And I will build a model, and I use that model, that cloud with a happy face, and I give it this as a new novel patient, and it'll predict for me, yes, it will reoccur or not. Okay? Make sense? So it fits in that framework that I showed you before. Here's another example. This is a true example, and it has been published. This is from our team also, U of A. So the idea is that we have a patient. She has breast cancer. After a biopsy to check she has breast cancer or not, we treated her with chemotherapy. But at the same time, we use microarray data to look at the gene expressions. And then we need to know what kind of adjuvant treatment we give her after the chemotherapy. So the hormonal therapy, for example. We need to know, is she estrogen receptor positive or negative? How to do that? Well, we look at all the patients that we know about their gene expressions, and we know whether they're ER positive or negative, and we will predict for this particular patient with this record whether they are ER positive or negative. And that will tell us whether we should use dexaminofen or not, for example. Okay, so this is very specific to this patient and not to another patient. And these techniques using machine learning are actually more accurate than the current techniques that we use to determine whether somebody is ER positive or negative. This can be used in many, many other things, like, for example, predicting who will develop breast cancer, who will predict if breast cancer will come back after we treat it, predicting who will will have a higher probability to reject this transplant, for kidney transplant, for example. Predicting the toxicity level for prostate cancer after treatment with radiotherapy. Predicting if somebody will lose muscle mass when they have this particular treatment after cancer, things like that. So all these can be done with the same approach that I just mentioned. And they're dedicated for a particular patient. Either with microarray data or with SNPs. SNPs are these basically, it's not gene expressions, it's the mutations that you have in the genes. The same thing can be done with nuclear magnetic resonance spectroscopy for analyzing the, like, for example, the urine test. This is to determine whether this patient will lose muscle mass. For the urine test, we look at the metabolomes that we have there, and we can, so we extract all of this information, we can build a model based on the previous patients that we have, and whether we observe that they had ataxia or not. So that's the classifier. The classifier now with this new patient will tell us yes, no, this person will have that. Okay. Of course, these classifiers will tell you probability, and then it's up to the physician to use that information. This is decision support. It doesn't take that decision itself, just helps the physician take that decision. And the same approach can be done for any any other disease. So you have a profile, will tell you, the classifier will tell you yes, no, they have that disease. Yes?
To what extent can we trust the machines or their probabilities in decision making, and how much autonomy should be relied on by the physician?
It's an interesting question. The final say should go to the doctor, but the doctor has to trust this. So how does the doctor trust this? There are two ways. This black box has to be able to explain why this person is predicted negative here, or why it is predicted positive. If the model is explainable, and I'll go back to that later on, I'll address it later, then the doctor may say, oh yeah, that makes sense indeed. Or they may say, no, I don't get it. Why is that? So I don't trust it, I put it aside. That's one way. The other way, this is unfortunately the typical way, is that in the beginning they're skeptical and they use it and then they verify if it is true or not, and after enough usage of the decision support system, if they see that in most cases it actually corresponds to what they think, then they will continue to just press the button and continue to use it. Does it answer your question? Yeah. But the trick here is to be able to explain the decision. This is what we call explainable AI. It's a new subfield within AI, especially in the recent years with the success of deep learning. Deep learning is showing, as I told you last time, showing results that exceed the accuracy of humans. So people want to use it everywhere, but now that it's being encouraged in many subfields, people are saying, yeah, but wait a minute, how do I trust this? I needed to tell me why I decided to go left or right. And unfortunately, deep learning can't. It's a real black box. So that created the subfield of explainable AI, trying to explain that. There are other methods that actually are explainable. Okay, and I'll show you, if we have time, 3 examples of machine learning, of approaches to deal with machine learning, and 2 of them are explainable, while I'll talk about deep learning, it's not explainable. We'll see why. Thank you for the question. Another example here, this is the case of diabetes. Diabetes, you know that there's diabetes type 1 and diabetes type 2. Type 1 is the, we don't produce insulin anymore, so the patients, we used to call it juvenile diabetes, but actually old people also can get it, it's not just juvenile. So type 1 diabetes, the patients have to inject themselves 4 times a day. They have to measure the level of sugar they have, and based on that and what the doctor told them, they will measure the insulin and inject themselves here, whatever, different places. It's a tedious thing they have to do. And each time they do that, they have a diary, they have to write there what did they eat, how much insulin did they inject themselves, what kind of activity they had, whether they were stressed or not, because the activity and the stress will change the consumption of sugar you have in the blood. So what happens, indeed, they write this, you see, they measure, they write it in the booklet, and then they go back to the doctor once every 3 months, or maybe once every 6 months, and in some cases they never go back to the doctor in third world countries. And it's the doctor that, looking at the diary, will say, actually, that formula that you were using to to measure your insulin is not right. Yeah, increase it or decrease it, because you don't want to have a hypoglycemia or hyperglycemia. So it's not perfect, because you have to go every 6 months to do that. The idea is to use, remember I talked about reinforcement learning. Well, you can do reinforcement learning to learn the appropriate policy. Remember, I talked about the policy, choosing the action to take to maximize the reward. So here it learns a policy to tell you what it is, the action is, what is the insulin level you should take to maximize my reward. What is my reward? Is that you don't have hypoglycemia or hyperglycemia. That's my reward. Remember, we're talking about this agent. The agent has a set of actions that it can take. It takes an action, it changes the environment. The environment is basically my sugar level now. And the observer, when you measure, will tell you, here's my state and here's the reward. You improved it or you didn't improve it. And this guy is trying to maximize that reward. That's how it creates this policy. This is an example of use of reinforcement learning in something like that for precision medicine. Here's another example. I'm showing you many examples. These are all in medicine because we are in the Department of Medicine. But later I'll show you other examples that are not in medicine at all that you're using today and you don't even know. This is an example with the Workers' Compensation Board. So when people are at work and they are injured, they go to the Workers' Compensation Board to be treated. It's insurance. So there's an injury, whether it's a back injury, leg injury, elbow injury, whatever. There's a treatment. After that first treatment, we do an evaluation to see whether this person should go back to work or we need another treatment to get them back on their feet to go back to work. So it could be a secondary treatment. We have another evaluation. And we iterate here until they're fine and then they go back to work. If this iteration here is too long, well, we lose time and money. Money because the company is waiting for this person to come back to work. And we lose money because we're treating, we're doing the wrong treatment, obviously. He's not getting better. So the idea is to help the assessors, here or here, help the assessors to recommend the best secondary treatment if necessary so that we don't have this long iteration. So what we do, we look at the logs of the patients that we treated in the past. There's some that have very long iteration, while others, immediately after the first treatment evaluation, boom, they're going to go back to work. That means we got the right treatment. Interestingly, we see many of these guys with very long iteration. It means that actually the human experts also make errors. They recommend the wrong treatment. It's not the treatment that is helping. And there are different reasons. Okay? It's not just the fault of these assessors. There are many reasons. Often there are psychological reasons. These people don't necessarily want to go back to work. And they want to take more rest and whatever. And it could be because there are treatments that are cheaper than others. There are treatments that are faster than others. There are many reasons. But anyways, we learn from these guys. And we build a decision support system that once a guy comes injured and is treated, the assessor fills a questionnaire. That questionnaire is given to the recommender system. So this is what we did here. We have an evaluation. It's given to the recommender system. The recommender system learned a model from the previous data, and then we provide that questionnaire of the new patient. And the recommender system will say, oh, that's the treatment that I would have. Okay? And then we have quick follow-up. And just to go back to your question about how do I trust this system, in this particular case, on purpose, we build a rule-based decision support system. The rules are learned automatically. It's not us giving the rules. It learns it by itself. Such that when the recommendation is given to the assessor can say, yeah, but why? And it gives the rules. And the rules are human readable. And they say, okay, now I understand why, and I give this recommendation. And actually, we had a very interesting experiment where we had 5 assessors around the table in a room like this, and we presented a case. We presented many cases, but each time we had a case at a time on the screen, and the case is basically the questionnaire that was filled. And we asked each assessor, okay, that's the case, this guy was injured by this, has this treatment, and here are the answers, what do you recommend, what do you recommend? They didn't agree. Each one was recommending something else. Then we said, okay, boom, here's what the computer recommends. Boom, here's why. They all are scratching the ears of their head, and yeah, yes, we go with that. Okay. So that was very interesting experiment.
I think that would weaken the functions of the doctor.
Not necessarily. That doesn't mean all doctors agree. Actually, sometimes it's actually powerful not to necessarily all agree. And it doesn't mean, even when they don't agree, it doesn't mean that they are wrong. And each case is different. But this one is also not necessarily completely consistent. Well, it is consistent, but it may, this system that I mentioned here, it recommends a treatment and tells you why, but it recommends another treatment with another reason, and each one has a different probability. And they may say, yeah, the first one is okay, but there are other conditions, so we'll go with the second treatment. It doesn't necessarily have just one treatment. Here's another example, completely different. And again, is to show you that personalization in medicine, so precision medicine, is not just about the genome. In this particular case, it's about doctors before doing brain surgery for brain cancer. They want to remove the cancer cells. They get these scans, and they're different layers, and they get the volume, and they have to segment on the screen the volume where they will basically operate. And it's a very tedious job. It takes about half an hour to do that. Half an hour of a doctor's time. And this is a specialist. It's not anybody. And what they do to segment this is not consistent. If you give it to two different doctors, they may give you two different segmentations, slightly different. The same doctor, in the morning and in the afternoon, they may give you two different segmentations. It's not an easy task to do. So to simplify this, we take all the segmentations that we have, we pass them to machine learning, it learns how to do the segmentation automatically. And then instead of giving the image, empty image, and then we ask the doctor to do it from scratch, we give it already pre-segmented. And then the doctor spends 5 minutes just adjusting it instead of doing the whole thing and spending 30 minutes. They spend 5 minutes. So it's helping them, and it's personalized to that particular patient. Here's another example, completely different. This is the case of detection of early signs of depression from text. So there's evidence that you can identify some signs of depression in text, what people write, and we're using models devised in psychology to basically identify different emotions, and we build systems to detect emotion in text, and we can trace that emotion, how the emotion is changing in time based on the different posts that people have. And we are still working on identifying, now we can identify emotions, we're trying to identify actually signs of depression, and we want to get them early on to help these people. Imagine it's in a school or whatever, then you can warn the educators to take care of this case before they become suicidal and things like that. Yes?
For that to work, though, wouldn't the person have to be like, can you look my tests? And
Yeah. There's also all sorts of safeguards in terms of privacy and given the authorization to do that and all that stuff. Yes. And my particular interest is a chat bot that we're building for the elderly. So you have a chat bot, imagine on within a toy, like the Sony dog, for example, or a teddy bear or whatever, and that person that doesn't want to go to the nursing home, want to stay at home, they're alone, they're bored. They may talk to a cat or a pet. In some places they're not allowed to have a pet in some condos and stuff like that. So they're bored, and boredom is bad for the elderly because that's when depression starts hitting. So the idea is to have this companionship, a companion that you can talk to, and that companion at the same time can try to detect these early signs of depression using these techniques. And obviously, you give your consent to do that if you're using that tool. I gave the example of students in the school. Yes, you need consent, and I leave it up to those who will use those tools to deal with that. But if you want to talk about ethics, it's an interesting one because what is ethical? Let's suppose I'm not asking them their permission, and I'm doing it and I'm saving their lives, or I ask their permission and then I'm not able to do it. I don't know the answer to that, but it's an interesting question. There is actually an interesting example that happened the last few years recently in Pittsburgh, where they were, you know, in many cities they have these kids, either they're troubled kids, orphan kids, or kids with troubled families. Social services will place them in another family, in a foster family. But these foster families are not necessarily ideal, especially with troubled kids. They have to check from time to time if it's the right place. If it's not, they move them to another family. I mean, it happens all the time. It's so serious that sometimes the kids die. Okay? If they're not placed in the right place, they can die. So these services go randomly check these families. Unannounced, they come knock, 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 and check the house. It's very intrusive. People don't like it. And they can't do it everywhere. So they do it randomly, or they have some kind of formula to do it. And what happens is they go and investigate a family where everything is fine. They disturb the whole thing. Or they miss families where there's trouble. So the idea is to build a recommender system, like I'm just talking about, that will tell you, hey, go and check that family, because there's a high probability there's an issue. Go and check that family. Okay? So when they started this project, people said, oh no, it's privacy. You're accessing data that, I mean, they didn't consent to use that for that purpose. They gave you that data to choose where to put the child, but not to do surveillance and monitoring. It was complicated to get all these papers done, so somebody, decision maker at a high level, said, no, we do it. We're going to do it. So they did it. At the end, when they implemented the system, they realized that actually they saved many kids. The number of kids that died went down significantly. And the question became, the ethical question became now, instead of, oh, can you do it or you can't do it because you didn't inform them that you're using this data for another purpose, now the question becomes, oh, can you not do it knowing that you're actually going to save lives?
So kind of like a cost benefit kind of thing?
It is an interesting question. I don't have the answer to these questions. But you definitely need to think about that. Yes? He's an expert in it.
Well, no, I just think it underlies a fundamental question with respect to all new technology, because we can see where it's going. The surveillance culture gives the possibility of intrusion, but it simultaneously gives the possibility of incredible good. If you think of criminal justice, you know, if you had surveillance everywhere, I'm sure we could reduce crime drastically. You know, so the question is, at what cost?
At what cost?
And I suspect you guys are going to be trying to balance that for years and years. But that's what we have to face both personally and as a society, you know, with policy. Because the possibility of doing good is only going to get better and better.
And we can't foresee at a time whether...
Yeah. And that's why it sometimes is who's going to wield it. You know, is it going to be good-hearted people thinking about the good of the population? Or is it going to be proprietary owners seeking to please shareholders? You know, those are the big questions.
Yeah, so we are now detecting emotions, typical emotions that people have defined in psychology. We're looking at other emotions that are, we believe, are related to depression, like frustration, disappointment, deception, feeling rejected, feeling betrayed, and so forth. Here's yet another example. This is the case, this is also at U of A, it was published. This is the case of treating people with bipolar disorder and people who have depression. They have the same symptoms. They're depressed, but you don't treat depression of a bipolar disorder the same way you treat depression with somebody who has depression. So you need to know that ahead of time. And we look at fMRI, and with the fMRI you can, you train it, you train the system with past patients that you knew, whether they were bipolar or just depressive, and then you build a classifier, and that classifier can tell you. And now we are trying to use the same thing to distinguish other disorders, like ADHD and so forth. So this is what I wanted to cover last time. This was my conclusion for last time. But I'm going to jump to more details about machine learning. Any questions? So some people ask me, I even got emails, some people ask me more details about machine learning and how it works. Imagine you have a child sitting here next to me, and I have a pile of balls, different colors, different sizes, different textures, different weight. So the balls have different characteristics. And I have buckets here in front of me, and I tell the child is now the computer, basically, you're representing the computer, but I say to the child, watch me, how I do things, and learn. I grab a ball, and then I put it in the bucket. What I did, I assessed some of the features, the weight, touched it, took the size, looked at the color, and then put it in the bucket. I don't say anything to the child. The child is only observing me. And the child is building in his or her head a model, that cloud that I was representing before. What is that model? It says, what makes me decide where to put each ball? After a few tests, after a few of these balls that I put in these buckets, the child will notice that actually it is the color that determines where I put the bucket. The size, texture, the weight were irrelevant. The feature that is relevant is the color, and that's what discriminates between the different classes. I have a set of classes. I don't have just two, cancer, no cancer, spam, no spam, or whatever. I have many classes. Okay? Doesn't matter, it's a general kind of model. After a while I stop the training, and I ask the child, here's a ball, put it in its right bucket. If that model that the child built in his or her head is correct, the ball will be placed in the green bucket. Make sense? That's exactly what I was showing before. So basically this is what we call, I'll go back here. This is what we call classification. I'm classifying these in different classes. We call it also prediction. I'm predicting in which bucket I will put that ball. Okay. It's like I'm predicting whether this disease will reoccur or not. Yes, no, I have two buckets. So visually what I have, this is when I moved my slides in this format, and they messed up the sizes of them. But here I have classes again, and basically I have my algorithm that goes over this and identifies what discriminates between the different classes and creates a model. That model now is used for objects that have never been seen before, and their labels are predicted. Okay? It's not as trivial as I'm showing you here. This is a very high-level description. There are many open problems at different stages. For example, what are the relevant features to consider? when I create the training data that I have to give it, if I don't give them the training data, their real features that discriminate, the model will never discover them. How do I represent them is also a question. How do I discretize, for example, a numerical value like ages? How do I put it in this interval, that interval? How do I present that data is an open question for many different problems. What kind of algorithm should I use to learn the appropriate way of discriminating between classes is also a problem. How to make it efficient so that if I have a lot of data, I can go through it in a reasonable time, not in 10 years. I want to do it in a few seconds. How to make it effectively and accurately and so forth. Now, how do I represent it here? That knowledge in the computer or in the head of the child, how do I represent it? And how do I represent it such that I can use it here effectively and be able to classify or predict accurately? Okay, so all these are interesting questions. They're not necessarily answered in all applications. And that's what the research is all about when you have a particular application. How do I do this? How do I do this? How do I do that? Okay. There are other interesting questions as well that we should consider. I mentioned the fact that when you go through this data, you create a model. In this particular case, how many classes do I have? 4. 1, 2, 3, 4. Yeah, 4 if I don't distinguish between these two, otherwise 5 because they're two different groups. So as many classes as I have labels, and this is what we call multi-class classification. My model here that I will represent here has to be able to discriminate between many classes. As opposed to this case, how many classes do I have here? 2, yes, no. Cancer, no cancer. Will reoccur, will not reoccur. Most problems are like this. In this case, this model is a binary class classifier. I'm just separating 2 classes. It's way easier than this case. Okay, so here I have 5 classes, here I have 2 classes. There's another issue. When I learn a model, here's the model that is learned, and I have new data that I need to classify, I need to predict. I can do it like I showed you before. Each one will get a label. I say that's a green, that's a blue, that's a red, this will recur, this will not recur. But there are some problems where when I have new data, I use the model, I don't assign just one label to each element. I may assign 2 labels. For example, I have pictures and I say, is there a dog or is there a cat? There's a picture that has a dog and a cat. I can't say it has just a dog. I can't say it just has a cat. It has both. Okay. Or, for example, these are documents. And I say, do they talk about this topic, that topic, that topic, and that topic? Well, this document talks about many topics. Okay? So I assign many labels. This is called single label classification. This is multi-label classification. It means each object I may give it more than one label. Here's another issue. This is what I talked about before. That cloud that is learned from this training data, okay, can be a black box. It means I just have to trust it as it is. I'll use it and it'll label the new objects. That's my cloud. But in many applications, like when you said, how do I trust this? That is not applicable. I mean, I can't use that. I have to have a transparent box I can see inside in terms of, for example, rules that I can read. So I can not only read, so it's readable, to convince me when it decides, yes, it has cancer, or yes, it doesn't have cancer, or no, it doesn't have cancer. But I'd like to be able to also write in it, change it. Why? Not all transparent, by the way, not all transparent models I can write. Some are readable, not writable, some are readable and writable. Writable, what does that mean? It means when I give it an object and it tells me, it predicts what label it should be, for example, it should have cancer, and I'll say, why? And it tells me, oh, I decided it has cancer because this, this, this. Why did it get this rule? It gets it from the training data. But me as a practitioner, for example, as a doctor using the system, I have other experience that is not represented in this training data. Then I may say, yes, but change this. And I inject my knowledge as an expert in the model. And then the model in the future will take that into account. And then that model is writable because I can inject my knowledge. Many models are not like that. Does it make sense? Yeah. I have two questions here. Yes?
Why would you want a black box? Like for transparent model, could I not do anything and it would also just...
Why do I want a black box?
Yeah. What case would it be?
Okay. When there's some applications where you don't care about why the decision was made. Suppose you're driving an autonomous car. You're not driving. The car is driving you. And the car decides to stop and then turn. Do you have to ask, why did you stop and turn?
Wait,
You don't have to.
Does it cost more to make a transparent model?
Yes.
Oh, okay.
Yes. It's more complex to do that if you want it to be accurate. So the most accurate techniques that exist today are unfortunately black boxes. And there are applications where these black boxes are fine, like I just told you about the car stopping. But for an application in medicine, when the doctor has to, well, the doctor has that responsibility to administer this treatment or not, I'm not going to say the computer told me. No, it's your responsibility. Then I want it transparent. You had a question too.
You answered it.
Okay, thank you. So we have some techniques that are in this realm, we have some techniques that are in this realm. Both coexist because sometimes these are faster to learn, sometimes these are more accurate, and sometimes these are more expensive. Yes?
So all deep learning is black box?
Deep learning is unfortunately black box. And people are working hard at making it explainable, but we're not there yet. They're black boxes. Particularly when they're making these architectures of the network more and more complex, it becomes even more complex to explain it. But when they make it complex, actually they become more accurate. That's the dilemma. There's another issue that is very important to keep in mind. When you provide data to learn, you assume, in most cases we assume, like here I'm using two classes, so it's a binary class classification. Assume that the representation is uniform, so it's the same, as many it's balanced. I have as many greens as I have reds, approximately. Okay, fine. And many techniques that are published, when they test them to say, oh, I'm better than the others, it's with cases like this. In reality, the majority of the applications, we don't have this luxury. Often we have more from this class than from the other class. For example, if I get data about breast cancer from a screening station. The majority of women going for the screening are fine. There are very few that have cancer. Okay. So it's completely balanced. So in most cases, in real applications, you have it like this. And you build a classifier, you build a model. You have to be very careful. Why? Also careful in measuring how accurate it is. Because suppose I have 97% of the green class represented here. I mean, 97% of my data here is from the green class. And only 3% of is from the red class. My prediction is and I can build a very accurate, very easily I can build an accurate classifier. Say green, 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 green all the time. I'm 97% accurate. So it's not a good measure. So here are applications I mentioned last time, spam detection, I talked about credit approval, when you get your transactions authorized with a credit card and things like that. So do we have time? We have a little bit of time. I'm going to show you how, again at a very high level, how some of these techniques manage to learn to discriminate between different classes automatically. I'll show you 3 different techniques. All of them are based on the same framework. So you have data that is labeled. Somebody has to label this data and give it to you. Okay, an expert tells you, well, this one has cancer, this one doesn't have cancer, this one has cancer, this one doesn't have cancer. It's given to the computer. That data is split into 2 parts. One part is used for training, one part is left aside for testing. I'm not going to use it for training, just leave it aside. I don't want to bias the training and testing. So from this training data, and typically, well, we split it like 10%, 90%, something like that. Can be 50-50, depending on how much data you have. Okay, so from this training data, you build this classifier. So this is the cloud that we had. And then you use that classifier here to predict what is the label of your test data. But you hide the label. You have the label, but you hide it. You predict it with the classifier, and then you compare with what you had from the expert. If they are the same, I'm accurate. If they're not the same, then you're not accurate. Okay. If the classifier accuracy is good enough for your application, you deploy it. If it's not good enough for your application, what do you do? Well, you go back, you use another technique for learning, you may do different splits, you get more data, and so forth. There are many different things you have to do. But you continue to do that until your accuracy is fine. Then you can deploy it and you have new unlabeled data, and that classifier will label it for you. What's a good accuracy? Depends upon the application. If my application is to detect whether it's spam or non-spam for my email, what's the risk that it's misclassifying an email? It may put a spam in front of me saying I didn't think it was a spam, so that's a false negative. Sorry, it's a false negative. And yeah, I'll be annoyed by it. It may have a false positive where you'll find an email that is good for me, but it thinks it's spam and it deletes it. Yeah, it's bad, but it's not as bad as telling somebody, hey, you have cancer, well, they don't. Or, worse, telling somebody, go home, you're fine, well, they have cancer. So then the accuracy, what is accepted accuracy is not the same. If my spam detector is accurate 85 or even 90%, I'm happy with it, I'll use it. But if my cancer detection program is accurate 90%, that's not good, I'm not going to use it. It has to be way more accurate. Okay? You see what I mean by an acceptable accuracy. So to build this idea of splitting, holding out some tasking thing, building this, it matches many of the techniques that we have, different paradigms. This is what we call k-nearest neighbors, decision trees, neural networks, Bayesian classifiers, associative classifiers, support vector machines, and so forth. There are many, many, many techniques. They all coexist. We don't just focus on one of them, because depending upon the application, one technique fits better than another. These days, this guy is becoming the winner. Now we call it deep learning. Winner in many cases. But it's a winner only if you have a lot of data. Remember that curve that I showed you? The more data you give it, the more accurate it gets, while the others hit a plateau. If you don't have a lot of data, that doesn't necessarily win. So now I'm going to show you, with the few time that we have, I'm going to show you these 3. And I chose these 3 on purpose. One, because it has the deep learning here, so that at least you have an idea about how it works. But because also these 3 are completely different, yet they reach the same goal. The goal is to make the computer automatically learn to do things without programming them to do it explicitly. So I'll start with k nearest neighbors. We call it k nearest neighbors, but I'll start with nearest neighbors. I'll remove the k. What is nearest neighbors? Nearest neighbors is a technique that is, we call it actually lazy, because it doesn't learn anything. It's lazy. You give it training data, the labeled data, say, okay, I'll rank them maybe or something, but I'll wait for you until you give me the data that you want me to label for you. Okay. And then when I give it a new object that hasn't been labeled, how does it predict the label? It didn't learn anything. Well, it predicts the label by choosing from all the data that you gave it as training, what is the record that is the closest to the one that you want me to label? Okay? So this is the training data. Here I'm using two classes, class white and class blue. I just store them. Now you give me a new object. I put it here red, it means it doesn't have a label. And say, I predict its label. I will choose among these which one is the closest. So I need to have a distance function that compares, for example, this patient with all the other patients. Which patient is the closest? And then I use that label of that closest neighbor and say, okay, I predict the label of this guy to be blue. Simple. Does it make sense?
Yeah.
Very simple. But it's lazy because it's not learning anything. We can make it a little bit more complicated. We call it k nearest neighbors because instead of taking the closest neighbor, I'll take the k closest neighbors. And k is something that you have to determine. Like for example here, 5. I'll take the 5 nearest neighbors. The 5 nearest neighbors don't necessarily have to agree on the label. I'll make them vote. Okay, so here I have 3 gray and 2 blue. Let's say it's a democratic kind of thing. There's 1, 1, 1 each. It's not a weight. You can have also a weighted kind of vote, but here's everybody gives a weight of 1. So I have more grays than blues, and this one become gray. Okay, make sense? You need to have the notion of distance between records. Yeah, you can have a weighted k nearest neighbors. There's other techniques, agglomerative nearest neighbors and things like that, but basically they're based on that idea. So that's one approach. Any question about that?
What does distance function mean? Sorry, I wasn't fully understanding.
A distance function, so you have, imagine you have records of, let's say patients. You need to have a function that given a pair of 2 of these patients, that function will return the distance between them. In the space, so it can be a Euclidean space, it can be any space, the distance between these 2, each record is a point in space, what is the distance between them? If I have that distance, then I can know for each record what is the distance to all the other records, I can rank them. Okay? And then when you give me a new record, now I can calculate the distance of this new record to all the other ones, and then see which one is the closest. I take that closest, what we call the nearest neighbor, and I take that label. And the distance depends upon the application in your case. For example, it can be the age is important, they live in the same neighborhood, same gender, whatever.
Yeah, so with these models, there's no like bias in the system. It's only based on like stratification, based on like one class and one number, right?
Yeah.
So does it have any real practical application when you're looking at, say, medicine, for instance?
Yeah, you can. Of course there are practical applications. Let's take the example of, I'm driving, self-driving car. I'm sitting, the car is driving by itself. The camera sees a sign. The sign is dirty, or maybe it's rusted and some of the paint fell. I need to recognize, is it a stop sign, or no entry sign, or no turn, left turn sign, or what sign is it? I have pictures of all the signs that I know. The closest image to that image Ah, it's the stop sign. It must be a stop sign. Make sense?
Yeah.
That's nearest neighbors. But I need to have the notion of distance between this image and that image. I have to define it.
Does the algorithm at all adapt to the environments?
The same approach is the same for comparing two records of patients or two signs on the street. What is different is the function, that distance function is different. The application will have to dictate what that distance is. The distance between two patients and the distance between two signs is not the same, makes no sense. I can't use the same function. I have to come up with another function. Yes?
Does it tell you, like, how close the vote is or the error possibilities of it?
The error.
Like, if it's like a close vote,
Yes.
then it would tell you.
You're
that-
talking about votes, so in this case here, when you have
Yeah.
this guy, yes.
So if it's taking lots of, if the K value is high, it's taking lots of neighbors to kind of judge what the best option is.
Yeah,
If it's-
so you shouldn't have a very large K if your space is sparse. When it's very dense, yeah, you can take a large K. But when it's sparse, it doesn't make sense to take many Ks because the Kth neighbor is actually far away.
Mhm.
If it's sparse, you should keep it a small K. But anyways, go ahead with your question.
So even in this example, if it's like a 3-2 vote, does
Yeah.
it tell you that it's quite uncertain about the final?
Oh yeah, it can, of course, it can tell you the result. Not only I chose gray, but it's 3 out of 5. It can tell you if my accuracy, no, not my accuracy, I'm confident. My confidence is 3 out of 5.
Okay.
Because that's different from 5 out of 5. All of them agree that it's gray.
Yeah.
Yeah, of course. And that can be passed to the decision maker. In addition to this label, we have this probability. Well, it's not really probability, but it's basically the agreement between the voters. Yeah. That information is there, so you can pass it. Okay. So here's a completely different approach. This is called decision tree induction. I'm coming up with a decision tree that will tell me how to distinguish one class from the other. So I'm using an example from the original paper that presented the original method called ID3. This is from Quinlan. He had this example with playing tennis, okay, just to illustrate his algorithm. So I'm using the same example. This dates from 1983, it's quite old. Playing tennis, he was playing tennis, and each time he played tennis, he took note of the weather outside. When he decided not to play tennis, he took note of the weather outside. So outlook, is it sunny, is it overcast, is it rainy? Then temperature, he puts it in different buckets, so hot, mild, or hot, mild, cool, okay, 3 values. Humidity, high or normal. Windy, is it yes or no? Is it windy or not? And then this class, will I play tennis or I will not play tennis? Okay. So now you can use this training data. I'm using different colors for the classes, so the no's are red and the play are gray. And you give it to the machine learning, and the machine learning will build a model that can predict when you will play, when you will not play, based on the past observations. Okay. So now that I have this training data, I can build something like this, decision tree. If the outlook is overcast, regardless of the other attributes, you can see whenever I have overcast, I play. Overcast, I play. Overcast, overcast, I play. I never have overcast and no play. So I can ask the question, okay, what is the outlook? If the outlook is overcast, then play. That's it. However, if the outlook is sunny, well, I have some sunny that are red and some sunny that are gray. So I don't know. then I ask, if it's sunny, I ask the question, is the humidity high or normal? And you can see that each time I have humidity high and sunny, then I will not play. And each time I have humidity normal and sunny, I will play. Okay, in this state. But what happens when it's raining? When the outlook is raining? Well, it's not the humidity that matters, it's the windy. I check if it's windy, yes, then I will not play. It's raining and windy, I will not play. But if raining and it's not windy, I will play. Now, this is my model. This is the cloud that I represented before. If you give me any condition, I will follow the path here, and it will tell me, will I play or will I not play. This is a decision tree. The tree helps me decide what is the class label that I should give. In this case, I have just two classes. What do you see here? Well, the tree, in computer science, trees are upside down. The root is here and the leaves are here. The leaf nodes are the class labels that you want to get, and each path in that tree is a particular condition that you have in your table. So any condition, you will find the path that leads to these leaf nodes, and it will tell you yes or no. Well, this is the class or that class. So here I have play or no play. It can be a medical record, and you have cancer or no cancer. Okay, it's the same type of thing. The question is, how do I build this? Is it the unique and only decision tree? Why did I start with Outlook? I should have started also asking the question of humidity from the beginning. Okay. Yes, question.
So it just like visualizes it to help you make the decision?
This is a visualization, yes. But there are many ways of visualizing this. I don't have to represent it as a tree. I can also represent it as a set of rules. And the rule is, if Outlook is sunny and humidity is normal, then do not play. So every path is actually a rule. And that rule, I can read it. So it's readable. Remember when I talked about readable and writable models? This is very transparent. It's not like deep learning. I can ask it, why do you tell me do not play? They'll tell me, oh, because it's windy and it's raining. So it can explain the decision. Okay. But the question is, how do I build this? Okay. So the algorithm that was presented in that paper is indeed talking about how to recursively build a tree. Because we can create different trees, and this is not the only tree, but there are trees that will be completely unbalanced. There are trees that are very deep on one side. You don't want a very deep tree, okay? Because if it's very deep, it means it's overfitting that data, and you have too many decisions until you reach that label. So you don't want it too shallow either, okay? But you want it balanced. So the recursive approach is to take to build the tree step by step. When you start on the root node, the first node on the top, you put all the data in there. And you say, okay, what is the attribute that best discriminates between the two classes from all the attributes? You select that attribute that best separates the samples into individual classes, and you split that node into two nodes based on all the values, possible values of that attribute. Not all the attributes have the same number of values. Like for example, Outlook has sunny, overcast, and rain, has 3. This one has true, false, has 2. Okay? So some will split with 3, some will split just with 2. Some may split with 10, or with whatever number of values, unique values you have in that attribute. So you create now new nodes for each value of that attribute. And in that node, you put all the records that were originally the root tree, but have that value for that attribute. And then for that unique node, you ask the same question. What is the attribute now, the remaining attribute that will split it even further? And you keep doing this, and you stop this recursion for each node when everybody in that node has the same class label, then you're done. You know that they have that class data. Or you don't have enough attributes to ask that question again, which attribute will split them? You don't have more attributes. You dealt with them all. Then you give a label from the majority of the records. So do you understand how this goes until you build this whole tree? The question is, how do I select the best attribute? And there are different techniques to find the best attribute that separates the records by class. There are techniques using information gain from the information theory. There are different techniques, but I will not go into details. So at least I gave you an idea about how this is built. Now I want to go to this neural network and deep learning. When it was introduced in the 50s, I said, well, it's like the brain. This is how the brain functions. That is a very naive way of describing how the brain functions. The brain has 100 billion neurons. You don't have 100 billion artificial neurons yet in computers today. It's very complex to do that. And every single neuron has thousands and thousands of connections to other neurons. But there's another peculiarity in the brain is that we have different types of neurons. We don't have just one type. We have different kinds of neurons. We actually have neurons also in the guts. I don't know if you know about that. Okay. This is the primary brain that we have in this body. The other major difference between the natural neurons and the artificial ones, the natural neurons are very slow. The computers are way faster. But where the natural neurons win is this immensely parallel kind of machine. Each one has 10,000 connections and you have 100 billions of them. That's why computers still have trouble really recognizing faces, but when you're walking in the crowd and you see somebody that you haven't seen for 20 years and you see them from the side and you recognize them immediately in a fraction of a second. It's impressive what the brain can still do, and computers can't. But where they are very similar, I will jump here first. So this is the artificial neuron. You have the body of the cell, but here I have the body of the cell. The cell gets not just one connection, it has many connections, so it's a vector here of input. Each one has a weight, and here you have dendrites sending messages, and they don't have all the same strength. They have different strengths, and that's what is represented here by weights. The cell, after receiving the message, at one point it decides to send the message through the axon to one or many, actually, other cells that will receive it from their dendrites. Okay? See, this one's sending this message here, and with the synapse here, it goes to the dendrite of this one. Okay? Here's the same thing. You have an activation function inside here that at one point will decide, when it sums this vector coming into it, this function will say, okay, fire this message. And the message can be positive, so it's exciting the next layer, or it can be inhibitor. It can be negative number too. It doesn't have to be, so some of these, they don't have to be exciting this one, it can inhibit the other one too. The same thing can happen here. That's where there's a resemblance. I'll go back here. So basically, the artificial neural network, you have these artificial cells, neurons, and they're connected to the next layer, and then to the next layer. So we have layers. One layer is known as the input layer, and one layer is known as the output layer, and in the middle you have these hidden layers you don't see. So the outside you see just the input and the output. Then you have hidden ones. And the message goes one way. You put it, the input goes in the input layer, these fire to the next layer, these fire to the next layer, and then they go to the output. So the message goes one direction. It's called feed forward. I feed it from here, it goes forward. These connections, as I said, have weights. So in the beginning, you start with some weights, they're random. And you learn, the learning is actually adjusting these weights. You adjust these weights such that when you enter, for example, a record of patient, this is the input, you enter the record of a patient, the output will say yes, no, has cancer, or doesn't have cancer. So in the beginning, it'll be a random number, and you say, no, I know that that patient has cancer because I have training data, they're labeled. Then you go and tell it, oh, you have an error here, you adjust these weights so that this is more to the yes or the no that you want, and these will adjust the weights until they go back. And we call it back propagation. So you propagate backwards the error to fix it. And you do it many times until all these weights will converge towards a number. Each one will have its own number, and they converge to their own number that will have an accurate prediction when I give this record in. Okay. And I do it many times. So this. Yeah. So this is what I was explaining. You see I have weights on all of these connections. And the algorithm that learns, most algorithms, are to adjust these going backwards. There are other algorithms that also add connections and remove connections. They're way more complex. But that happens also in our brain. When we learn, we actually create new connections. With time, we create connections between neurons. So this is my input. See, I have some attributes and values, and I have a class label. For example, cancer, no cancer. I keep that aside, and I take this information, and I pass it as input. I propagate the information, the weights. When it comes out here, I compare it with my label. Did I get something that is exactly like what I want? No, because it was more or less random in the beginning. Then I will, after I compare, I'll send back, do I have, yeah, I do, there's a reinforcement to adjust the weights. It has nothing to do with reinforcement learning, but I reinforce it using, well, adjust the error that I have between what I wanted to get and what I actually got, and I propagate it backwards. It's called back propagation. Okay, that's the most commonly used technique. There are many other algorithms, but this is the most popular one. And it's easier to implement, particularly now in deep learning, because you don't have just one layer. Remember yesterday I told you that in the olden days we were not able to put many of these cells in the computers that we had. With the computers that we have today, we're able to create very complex networks, and we have many hidden layers, and we call it deep learning.
Who would adjust the weight? The computer itself or
The computer, yeah, because all this training data, you will enter it one record at a time, and suppose you have 1 million records here. After you enter them all, you do it again. You do it again. Each time, we call it an epoch. And we do like 100,000 epochs. So it can be done manually. It's all automatic. It takes a long time to train. This is
so
one
the human already says the program
The
already.
human only gives me that label for each patient, for each record. And again, this is the ball. The ball, this is the bucket where it should go. It's exactly the same example I showed you before. These are, for example, the weight, the structure, the color of the ball, these are different features. This will learn automatically that only the color matters. All the others are irrelevant. How does it know it? Because it will connect here, it will add weights where the color is relevant, and the weights for the other connection will become almost zero. So it will learn automatically the features that matter. By doing it many times. I have to scan this and enter through this here many times, and adjust the error again and again each time. So there are techniques that adjust the error for each record, and there are techniques that adjust the error for each batch of records. So I pass this batch of records and see the error and then propagate it back. So there are many advantages and disadvantages of this technique. The main advantage is that the accuracy is typically quite high compared to other methods. It's very robust, even if you have noise in your data. After a while, it will converge. The negative things is that it takes a long time to train because you have to do all these epochs. Each time you have to go through the whole data set. It's very difficult to understand. So what is the model that we learn? This black box is all these weights. If I go and change the weight of one of them, I have no idea about the impact of that. So if I have knowledge that wasn't represented here and I want to inject it here, I have no idea how to inject it. In the case of the decision tree, if I have knowledge, extra knowledge, I can add it here. I can adjust the tree. And I know the impact of this adjustment. Here, even though it's way more accurate, that's it. It's a black box. I can't change it anymore. Okay? Another disadvantage is that how to design the network, which node connects to which node, and that graph can be very big. It's an art more than a science. It's very complex, very difficult to do. There's a lot of trial and errors. You have to try different architectures. If you make it too small, it takes a long time to converge to something that may work. And if you make it too big, then you have very poor performance. So what size you do it is not that easy to do. And deep learning is basically the same idea, but you have a larger number of hidden layers, and it inherits these advantages and disadvantages. Okay, this is a slide from last time. I talked about this. I want to talk about other. Do we have time? We don't have time. I think I'm going to stop here. I can talk about many other applications, like for self-driving cars, like recognizing characters. I talked about spam and authenticating these transactions. There's also financial applications to detect fraud. There are adaptive interfaces, whether it's for recommending products or adaptive interfaces is also like Facebook and other interfaces you're using every day. But I'd like to give you the chance to ask me questions. I'm starting here. Yes?
So do we build a neural network? Like we made the decision tree, right?
A neural network and a decision tree are two different things.
Do we make the layers? Like do we decide how many layers?
We humans decide about the layers.
Yes.
There are algorithms in the olden days, but they are not used now, to automatically add nodes in the layers. But today, the deep learning, the designer decides how many layers we're having and how to actually specialize also the layers. These convolutional neural networks where we have layers that specialize.
So when you say learning is just the ability to adjust weights?
Exactly.
Okay.
Learning is only finding the right weights that will give you the right outcome that you desire based on the training data that you have.
And adding to that, is this also a recursive process to create this these layers?
No, the recursive process is for the decision tree.
Only for the decision.
Only for the decision tree.
Okay.
In the beginning, you have no tree whatsoever. You have only the data, and I'm trying to decide which attribute I should use to split, which attribute to split. The tree has nodes. Each node represents an attribute, which is different. The nodes in the graph or neural networks, each node is actually a cell.
So then how do you dictate these synapses between these, between the layers? Like how do you know how to optimize the synapses so that it's connecting to the right?
That's why I'm saying it's more an art than a science. and you have to try different architectures to see which one is the best. And, I mean, you can start with a fully connected graph, but that's an overkill. So it depends upon the application that you're using. If you're dealing with images that you're trying to analyze, or is it text, or is it records of patients, different architectures would fit better this application than that application. Yes?
So we make the layers, but within the layers there's so many nodes, right?
Yes.
So do we
How
also?
many nodes are in each layer? There are different kinds of architectures again. There are some where you can confine them into, like what we call an autoencoder. You confine them into a layer that is narrow, a hidden layer that is narrow, and then you open them up again. So it's like compressing the knowledge and dumping all the attributes that are irrelevant. While in other cases, the hidden layer is actually bigger. So you go bigger, and then I don't have a general answer to tell you how to decide. It depends upon the application that you have, and you have to try different possibilities to see which one works best for that.
And I also saw like there's one node could have 3 connections, one could have 2. Do we decide
Yes.
that again, or is it?
Yes.
Oh, so we made that as well. Okay.
Yes.
Oh, I don't know. Okay.
But a connection goes from one layer to another, it doesn't jump.
Yeah. Okay.
So when neural networks started, they didn't call it actually neural networks. Often we use the term connectionism for the field of neural networks, the science of neural networks. And people have tried different architectures where they learn also new connections, and they sever connections. They increase the size of the hidden layer automatically. But those algorithms were too complex and too slow, and they didn't lead to something substantially better than what we have now. So people gave up on that. We may come back to it, because the human brain, we have connections that form. We don't have new cells. We know that we lose cells as we grow older, but we have more and more connections. So having an algorithm that learns automatically to find new connections is interesting. But it's a complex algorithm to do. Other questions?
So like the best way to have like 1,000,000 connections per node, because then it can always set a weight of 0 if it wants to delete.
Yeah, but it takes longer to learn.
Yeah,
Too.
that's yeah. Okay.
You have to find a balance.
Yeah, yeah.
Yes.
So I know you said that it's non-editable, like you can't change the program after, but can you still change, if it's dealing with new data, not the training set, can you still tell it that it was right or wrong so that it can go back and...
Yes, that's what the learning is.
Okay.
So the learning, in the case of a neural network, you have your training data, you have the label, you didn't put the label in the input. In the input you only give the record itself. You keep that label so you see the output, and then you compare, you say, hey, you made an error. And it fixes the error by going backwards, by adjusting the weights. So that's exactly what the learning is. Okay. Well, thank you. I'll see you next week.